Okay, let's see. All right, good afternoon. Can you all hear me okay? Microphone's working? Okay, great. Well, good afternoon and welcome. My name is Neil Garg. I'm a professor of chemistry. I'm also the current chair for the Department of Chemistry and Biochemistry. And it's really my great pleasure to welcome you to our first distinguished lecture of 2020, our first distinguished lecture of the decade. And this lecture series, just so I can give you a couple of introductory points, it's intended to feature the most preeminent scientists in the world. And the speakers we invite have made scientific contributions that extend across traditional boundaries and address many of the most exciting and challenging problems that we face in society. And so today, our speakers are our very own Executive Vice Chancellor and Provost, Professor Emily Carter. And so Emily, thank you for making the time. I know you're an extraordinarily busy person, and I think we're all delighted to have the opportunity to hear about your science, of course, and I think more generally, I think we feel very lucky to have you back at UCLA. So thank you for coming back. We appreciate that as well. And so Professor Carter will present her lecture in just a moment. In addition, I just wanted to mention that right afterwards, we have a reception in the CNSI lobby, and you are all very much welcome to attend then. We encourage you to do so. So I will now turn over the podium to my good friend and colleague, Professor Bill Gelbart, who will introduce Professor Carter. Bill.
It's a very special pleasure for many reasons to introduce our new Executive Vice Chancellor and our once again colleague, Emily Carter. Going back a few years, Emily did her undergraduate work at UC Berkeley, her PhD thesis work at Caltech, at which point, and this was 1987, she was already a star in the theoretical chemistry world. We were lucky to hire her as an assistant professor then and have her as a colleague for over 15 years as she rose fast through the ranks to become one of our very best teachers and one of our very best researchers. Even though she and I did very different kinds of theory, we quickly became friends as literally across the hall neighbors in the department, but also as almost across the street neighbors at home. Emily's work centered from the beginning on the development and application of new theoretical methods for determining the electronic structure, chemical properties of a broad range of molecules, clusters, surfaces, and materials. After accepting a position at Princeton University in 2004 as professor of mechanical and aerospace engineering and also of applied and computational math, she continued to work on orbital free density functional theory and ab initio simulations of chemical reactions in solids and at surfaces. But her interests also turned to the challenges of renewable energy. In 2006, she became the Arthur Marx Professor of Mechanical and Aerospace Engineering and of Applied and Computational Mathematics, and in 2009, co-director of the Combustion Energy Frontier Research Center, and then founding director of the Andlinger Center for Energy and the Environment. During this time, her work was recognized by many major prizes, including the Theoretical Chemistry Prize of the American Chemical Society and the Langmuir Award of the American Physical Society. She was also elected to the American Academy of Arts and Sciences, the National Academy of Science, the National Academy of Engineering, and the National Academy of Inventors. I don't think there are other possibilities. She's surely one of only a small handful of people to be multiply honored in this way. In 2016, Emily was appointed Dean of the School of Engineering and Applied Science at Princeton, where it became all the more clear that she isn't just a great teacher and great researcher, but also a great administrator. And all of this is very lucky for us as she returns to UCLA to lead the university as Executive Vice Chancellor. More important than her being an exceptionally efficient and effective administrator, Emily is someone who has always insisted on, and now no less than ever, on the highest standards of excellence for herself and for everybody around her. And that means all of us at UCLA. She also brings a vision for and a commitment to renewable energy, protection of the environment, and university community collaboration to improve more generally our quality of life. I'm confident that she's going to be the best executive vice chancellor UCLA has ever had. Emily, once again, welcome, and thanks for coming back.
Well, that may be the most beautiful introduction I've ever had, so thank you, Bill. It's really a pleasure to be here. There's a few seats up front if you would like to come down. I don't bite, so please do. And there are seats over here as well. So it's really a pleasure to be back. It feels very strange to be in this building, which I was part of designing. I like to say I was involved in designing a bunch of buildings at UCLA that I never occupied, so the height of altruism. Anyway, I'm here to talk to you about my research, which actually feels terrific. I have to sort of now I'm taking off one hat and putting on another, and I have to say this is, this has been my raison d'etre for most of my life, and so it's wonderful to be able to come talk to you. It's a form of therapy for me. How's that? Okay. And I am trying to juggle both balls, or many balls, including the university, running the university. But in addition to keeping up my research, a lot of the work that I'm going to talk about today, not exclusively, will represent the research of one extremely talented, special individual who is in the audience. And his name is Dr. Marc Martirez. And he is an assistant project scientist. He's the one member of my research group that said, LA, I'm coming, okay? The rest of them are still back in Princeton. So, but Marc has done extraordinary work with me over the last few years. And I'm really happy to tell you about a lot of his work and the work of some others as well along the way. So we're going to talk today about a couple of projects that actually, well, 2 and possibly 3 bits of projects that have to do with how one can think about using renewable energy to do chemistry. Because this is a chemistry talk. So I'm going to focus on that aspect of my work. And we're going to talk about artificial photosynthesis mechanisms and how we can potentially optimize materials and molecules that functionalize those materials in order to optimize their efficiency for chemical conversions. And it says from first principles, and that's referring to what Bill Gelbart mentioned, which is that we, in my group, have spent many years developing and applying quantum mechanics methods to simulate various kinds of chemical and materials phenomena. Okay, I have one slide to show you. As Bill mentioned, a lot of the time that I spent at Princeton, I was there 15 years, and essentially the last dozen years I have focused very intentionally on how I can use my expertise and the tools that I've developed and that others have developed to really contribute to developing new sustainable energy technologies. And so I'm going to show you one slide that gives you a sense of the kinds of breadth of projects that we have worked on, and I'm going to then zero in on a couple of those to tell you about. So when you think about renewable energy, you have to think about both electricity and fuels, and also energy efficiency, frankly, when you think about sustainable energy. So in terms of electricity, we had several projects, one related to, whoops, sorry about that, one related to actually thinking about, and Bill mentioned that I spent actually a couple decades developing orbital free density functional theory, a very fast algorithm for solving for electron distributions and energies mostly in condensed matter. And it turns out to be was a quite useful tool to look at liquid metals that are being looked at the Princeton Plasma Physics Lab as a possible first wall material to essentially withstand neutron fluxes that will happen in fusion reactors. So we just finished up a project related to that. So fusion, of course, maybe long term by the end of this century will in fact contribute to in some substantial way to our electricity production around the world. We also work on alternative solar cell materials. This is a project that, in fact, is just coming to conclusion. The idea is, of course, we have silicon-based solar cells. We have others as well. But how could we potentially come up with even cheaper, more efficient, and easy to process and costing less energy to produce solar cells? So we worked on that as well. We also worked on optimizing materials for so-called solid oxide fuel cells, another way of producing clean electricity using these particular kinds of high-temperature fuel cells. I'm not going to talk about any of that because it's material science, it's not chemistry. So we also had projects related to biofuel combustion. That was, Bill mentioned that I was a co-director. I was the scientific director of the only Energy Frontier Research Center funded by the DOE on combustion. But that's chemistry, but I'm not going to talk about that. It's old work. I like to talk about more recent work. And then we also used our orbital free density functional theory method to look at mechanical properties of lightweight alloys to try to help optimize alloys that could be used to lighten the weight of vehicles to improve their fuel efficiency. So these are really about cleaner, more efficient forms of transportation. Now turning to fuels. So in fact, this is a project I will talk to you about, which is related to artificial photosynthesis, and it's using sunlight, light that shines on a semiconductor. This is a cartoon I'll come back to later, but it's Photoelectric Catalysis. So that work is still ongoing in my group, ways to convert carbon dioxide, for example, to methanol. And methanol then can be converted to many other things, and also to oxidize water. Another one that I hope I'll get a chance to talk a little bit about at the very end, because we have essentially the only method in the world in terms of a quantum mechanics method that can properly treat the phenomena involved with having light that's not absorbed by a semiconductor. That's sort of the usual thing one thinks about, is light being absorbed across a HOMO-LUMO gap or a semiconductor gap, but instead having light being absorbed by small nanoparticles, metal nanoparticles. I guess that's appropriate to be talking about in the Nanosystems Institute, now that I think about it. And the point is that you can have light of different tunable wavelengths depending on the size of the nanoparticle to absorb that light and excite what are called plasmons, which are collective excitations of valence electrons. And when those plasmons decay, and there's a bunch of different routes to their decay, one of the things they can do is produce excited states, essentially localized excited states, electron hole pairs. And those electron hole pairs can do chemistry, okay, just like the electron hole pairs in a semiconductor can do chemistry. And so we have methods that can look at those excited states on metal surfaces that can describe that process. I hope I'll get to that at the end of the talk. Two other more recent projects that started in the last couple of years. One is, again, basically, in this case, taking, in this case, this is a high temperature route using absorbing concentrated sunlight by a metal oxide, not in the same way that you have a band gap here, but just essentially driving off oxygen from a metal oxide that then produces a metal suboxide that wants to grab oxygen from something. And so what you can do is introduce water and carbon dioxide and essentially get syngas out. Okay, so you can get CO and hydrogen out. So we're working on optimizing materials for that as well. And then lastly, this is very new, and this is work that is in collaboration with a team of people to look at materials for doing water desalination. So that's not energy, but of course it's very important to our future. So how do we do it? So this is a one slide to just give you the sense of how somebody in my world thinks about how to approach those kinds of problems and how to characterize the chemical transformations and the materials properties of all of those materials and molecules. And that is, we start with the basic laws of physics, namely quantum mechanics. So I wish that was me. It's not me. But you start with the fundamentals that you learn, and then what you do is, as all of you in this room probably know, you have this lovely equation called the Schrodinger Equation, which is a beautiful equation, but of course it can't be solved exactly except for very simple model systems. And so what one has to do is be clever about the approximations one introduces to not do violence to the physics that you're trying to model. And so one comes up with essentially approximations to this equation that you write down with pencil and paper. Then you create computer code. You stick it on a supercomputer or a laptop these days. And out comes results. So this is actually now a paper from now 9 years ago or something. It was one of my first papers associated with thinking about solar energy conversion. And it just gives an example of both of the fact that you get out an energy, E, as a function of some parameters. So these are we have these parabolas here that are representing different electron energies. And out of that also, the wave function, this psi, gives you a distribution of the electrons. And so this is showing you a picture of the distribution of an extra electron in silicon-doped hematite, for those of you that care. And doesn't matter. It's just to give you a sense of what comes out of the process of doing this work. And so what comes out is both energies and electron distributions and also forces on the nuclei, so forces on the atoms. And that allows you then to look at materials properties and dynamics and get insights. And so that's how we do our work. So with that, I'm going to start telling you about one very important problem. There's, you'll be, well, should I say this? No, I won't say this. I'll just say that there are people that are walking around feeling very righteous that they drive hydrogen fuel cell vehicles. And I immediately stop them and say, you're walking in on the middle of the movie, okay? Because hydrogen, we use hydrogen for many things. We use it for in industry for ammonia synthesis and hydrotreating and lots of different things, as people in this audience certainly know. But the problem is that 96% of the hydrogen actually came from steam reforming of natural gas, which produces CO2. So all those righteous people are saying, oh, I've got this car that only produces water as a byproduct. Well, the problem is that all the hydrogen they used already produced the CO2, just not at their tailpipe. So that's a big problem. And so it's really important to be thinking about ways to get to renewable hydrogen that doesn't produce CO2. This is stolen from a DOE website. So given here, energy.gov, it's somewhere on that website. Anyway, the bottom line is that right now we do natural gas reforming that produces all this CO2. Whole bunch of different ways. I told you about some of them on the previous slide that one can approach it. What we're going to focus on is electrolysis. So the idea is you start with either solar or wind. I don't care. I'm agnostic. I just want some form of electrons that didn't come from making CO2. And then I'm going to ask how those electrons can be used in an electrochemical cell in order to produce renewable hydrogen. And so here is what we can think about in terms of electrochemical water splitting. There are two reactions. There's the cathode reaction, that is the reduction reaction that produces hydrogen. That I'm not going to concentrate on because that's not the hard bit. That we know how to do. What we don't know how to do so well is a 4-electron oxidation, basically taking water and oxidizing it to O2. Or this is written in terms of hydroxide. It doesn't matter. And so the question is how to do that well. And here are written some of the challenges. The reactions are slow. It's a 4-electron oxidation. You have problems with the electrode in terms of it degrading or being poisoned. If you have, for example, ions, it can be non-selective. So you can't just stick seawater in there and expect to get out oxygen and split water. It'll oxidize chloride and make chlorine, for example. So how do we go about thinking about this problem? Well, in fact, as I already said, the anode reaction is rate limiting, and we know that one can do it well and even do it selectively if you use very, very precious transition metal oxides such as iridium oxide and ruthenium oxide, or to use platinum. And so there's a lot of interest in finding cheap alternative catalysts that could be widely deployed, because you're not going to widely deploy those catalysts very easily. And so there's been a lot of work looking at metal oxyhydroxides. So I'm not suggesting something new here in the sense that lots of people are working in this area. What I'm going to tell you about is I think that we really understand why these materials work and how certain ones in particular work, and we think we're on to how to improve them. So these materials are layered structures. So I'm sure probably everybody knows about graphene. That's one kind of layer structure, or polysulfide. This is another one, metal oxyhydroxides. They're bound by hydrogen bonds. Each layer has these edge-sharing octahedra, metal octahedra, and they're approximately hexagonal. The lattice is approximately hexagonal. Now I have one slide that shows essentially a summary of some experimental data to give you a sense of where we go from here. So this is a series of these metal oxyhydroxides with different first-row transition metals in the mix, either pure or mixed together. And what's being plotted here is the so-called overpotential, which you can think of as essentially the kinetic barrier. And then there's the turnover frequency, the catalytic turnover frequency, which is essentially the rate. And so what you can see from this then is that you want to get to high turnover frequencies and you want low overpotentials. So the best one is this one in blue, and that is actually iron-doped nickel oxyhydroxide. So that was found by accident, okay? As many as people in this room know, that often happens. And the question is, why is it that is so special? And I'm going to be able to answer that today. So there had been work before we got into this theoretical work looking at a particular facet of this. I'm not going to talk about it except to acknowledge that there was work going on prior to ours. And then looking at, for example, an electron micrograph of what these structures look like. It turns out that it comes from a hexagonal lattice, and so that also shows up in the morphology of what forms. You get hexagonal nanoplatelets. And so Mark, who I said was sitting in the audience here, what he did with that information was to do a very rigorous, really the first rigorous study to look at the different facets of this material, the nickel oxyhydroxide, and in the presence of water, and to then use the information about the interfacial energies to do what's called a Wolf construction in order to be able to say what the most stable crystallites would look like. And so that work was published now a couple of years ago. Bottom line is we then did a bunch of work looking at the dominant facet, which is the basal plane, but also looking at a facet that had not been looked at at all, that is a minority facet, but it has enough of low coordination iron that we thought, or when it's doped with iron, or low coordination nickel, that it could in fact play an important role. Because as we know, if you have a coordinatively unsaturated metal, that tends to be more reactive. And so it's the case that even if we could see a reduction in the overpotential of 1/4 of a volt, that could lead to over a 10,000, 20,000 fold increase in the rate at room temperature. So even small changes in that overpotential make a big difference. So Mark did a lot of work to look at a whole variety of different possible mechanisms and then to try to sort out what was going on. And I'm going to just show you 2 slides about this. It turns out that what we discovered is that you start with this surface that has an iron hydroxo, and that iron hydroxo then can essentially get oxidized, losing a proton and an electron, to form this iron oxo. It's an iron 4 oxo species, and then it undergoes further oxidation to release oxygen in the overall step to reproduce another state of an iron hydroxo. Breaking that down, what happens actually is that this iron oxo attacks a lattice oxygen to form this O2, this eta two O2 species. And then, in fact, what happens is that the formation of this dioxo species reduces two of the nickel 3s that are in this material to nickel 2. And that turns out to be very important. We're going to understand why that helps facilitate the reaction in a little while. Then water gets absorbed, and then the water essentially then deprotonates, and the system becomes more oxidized. And the electrons from the release of O2 actually then have the iron 4 getting reduced back to iron 3. And that's the kind of catalytic cycle that takes place after continuing. We have to get it back to its resting state, which is achieved by the positive bias of the electrochemical cell to reoxidize nickel 2 back to nickel 3. And that's what happens in this cycle here. So with that, that's a lot of detail. I don't expect you to remember much of it at all, but I want you to understand that then you look at this and you look at the actual free energies, which then are converted to voltages, to get a sense of what is the overall overpotential. And from theory, you get the overpotential by taking the highest, so kind of like the rate limiting step, the highest barrier, but this is thermodynamics, so it's the highest free energy change, the highest voltage, and subtracting off the thermodynamic potential, which, as many of you probably know, is 1.3 volts. And that leads to an overpotential that is the lowest that has been predicted ever, and it's 0.14 volts. And what that gives us, because this is all thermodynamics, is a thermodynamic lower bound. And the beauty of what Mark did is that if you compare that to experimental values for these iron-doped nickel oxyhydroxide are higher than that. So that's important because this is a lower bound, and it's higher because there is a bit of a barrier, no doubt, somewhere along the way, and that's why the experimental value is 0.2 to 0.3 volts. Contrast this with earlier theoretical work, which said, we were able to calculate an overpotential that matches experiment of something like 0.25 to 0.3, 0.35 volts or something like that. That's not physically correct, right? It has to be that what the theory produces has to be lower than what's measured experimentally. So this is one reason why we believe that this particular kind of active site is really critical to do this kind of work, this kind of conversion. Contrast this to what happens without the iron. So here, this is the pure nickel. It was known that iron doped, as I showed you, is the best catalyst, and without the nickel, it's much less efficient. So that means the overpotential is much larger. Well, it turns out, you might think, well, it's just because you substituted iron, and iron is somehow fabulous, right? That's part of it. But it's not that simple, because it turns out it's not that it goes through the same mechanism. So again, this is beautiful chemistry showing that you have to not just look at one mechanism, but a multitude of mechanisms to try to figure out what's really going on. And Mark did that, and what he showed is that, in fact, the most favorable mechanism for the pure nickel oxyhydroxide doesn't go through that metal oxo species. Instead, the oxidation produces a dihydroxo species that then makes a hydroperoxy species, which then releases O2. So a completely different process of redox chemistry than what goes on in the case of iron. And I won't go through the details of that, except then what we can do is, again, look at what do we end up finding in terms of the overpotential. Well, Mark calculated an overpotential of 0.48 volts. Again, experimentally, it's 0.6 volts. So we are at that lower bound. So it gives us great confidence that we actually have nailed the mechanism. In fact, if you ask the question, well, what would have happened if you tried to create a nickel oxo species? Here it is. You could make potentially, you can do this on the computer, an oxyl radical, okay, a nickel oxo. But notice the voltage. The voltage is much higher than the voltage to make the cis dihydroxo. So it's very unfavorable to make this nickel oxo species. So those are the results. But as I told you, it's not just about, and this is what I always told my students and postdocs, is it's not enough to essentially elucidate numbers. You have to understand what the numbers mean. You have to get out the insights that allow you to then extrapolate and be creative about creating new materials and new molecules that have different kinds of chemistry. So here is an explanation of why that's going on. So we want to understand what is it that explains the activity of the iron-doped nickel oxyhydroxide. It really, what it has to do with is that you can make, as I've already said, you can make an iron 4 oxo, but you can't make a nickel 4 oxo. Why is that? Well, here's a simple molecular orbital diagram. I'm not going to go through why that's the order. That's crystal field theory. And now let's just look at the occupation of an iron 3 plus ion, an iron 4 plus ion versus nickel 3 plus and nickel 4 plus. And these, by the way, these occupations, they're not just arbitrary. These come out of the electronic structure calculations where we can calculate the magnetic moment on the ions. And so that tells us how many unpaired electrons are present. And so it turns out in the case of nickel, you don't make high spin nickel. Okay, so actually it's a low spin nickel that is present in these materials. Anyway, why is that important? It's in fact incredibly important, because if you look at the iron 4 versus nickel 4, the difference is that in the case of nickel, the pi star levels are 100% occupied. And this is a picture where you think about O double minus as the oxo ligand. And so its pi's are occupied as well. And so what you have essentially is a very unstable nickel oxo situation, whereas here you have unpaired electrons in the pi star level. So it actually has a bond. This kind of picture goes back to actually to work I did as a graduate student of bonding that looks like the same kind of bonding you have in the dioxygen molecule, where you have a pi resonance going on. And that's what stabilizes this iron 4 interaction. And nickel 4 can't do that, so instead it makes this nickel dihydroxide. It just goes another way. So that's what iron does. That's why iron is so special, because that sets up having the oxygen that you need to attack a lattice oxygen that makes the O2. So that's why it works so well. But then the question is, what about the whole oxidation step itself? Well, it turns out if you think about nickel, and one of the things that was true on the previous slides is that I didn't emphasize, but nickel favorably reduces from +3, so here's the +3 state of nickel, to +2. It turns out that it goes from this state that is this low spin nickel 3, it goes to a high spin state in the nickel 2 plus during the catalytic reaction. Whereas iron 3 plus doesn't want to go to iron 2. Why is that? Again, fundamental insight actually from quantum mechanics. If you think about going from this high spin iron to adding a low spin electron to make iron 2, in fact, all you gain is an electron-electron repulsion by putting those two electrons in the same orbital. On the other hand, for the nickel 3 plus going to nickel 2 plus, you've gone to this high spin nickel 2. Why is that good? Because not only do you have, you're not doubly occupying this orbital here, that's one point, but you also gain so-called quantum mechanical exchange interactions that actually lower the energy of the system by going to this high spin state. So nickel 3 to nickel 2 is extremely favorable, but iron 3 to iron 2 is not. Another way to think about it is it's the stability of the half-filled shell of the D5 state here. Doesn't want to add an electron. So in fact, both iron and nickel play these very symbiotic roles in this material. Iron 3 is the place that can make this O2 by forming first this iron oxo, whereas nickel 3 plus essentially can pull electrons out of water in order to make nickel 2 favorably, whereas iron 3 can't do that. And so it's a really beautiful way to understand why this iron-doped nickel oxyhydroxide is so much more favorable than any of the pure materials. If we think about, and the plot I showed you of overpotential and turnover frequency had on it, pure iron oxyhydroxide. Problem is that this iron is iron 3. And I just said that iron 3 is not easily reduced. So it can't easily oxidize water. So you can't even get the process started as easily as you can when you have the nickel oxyhydroxide. But nickel oxyhydroxide is not so great because you can't form this very reactive oxygen. And so it can't produce the O2 easily. So you have this Goldilocks situation where iron-doped nickel oxyhydroxide allows you to form this reactive iron oxo and having it in the host of this reducible nickel-3 that can pull electrons out of water is what allows you to have this facile water oxidation. And in fact, we have work going on ternary oxides to take advantage of these insights to improve the process further. Enough said on that. So now I want to turn to talking about photoelectric catalysis. What I've talked about so far is electrocatalysis for renewable hydrogen. I want to now spend some time talking about CO2 reduction. So this side of the equation. And now thinking about thermodynamics, we're actually going to be thinking about thermodynamics here and kinetics. But for thermodynamics, what you need to understand is that any reaction, that one of these redox reactions, as we just talked about, has a certain characteristic amount of free energy or voltage that you're going to have to apply to make it happen. Well, in the photoelectrocatalysis, the idea is you have some electrode, semiconductor electrode, that can absorb light, form these electron hole pairs, and on the cathode side, because we're going to be looking at CO2 reduction, that electron can drift if it's close enough to the surface, the interface between the electrode and the electrolyte, that this is the conduction band minimum. The electron gets boosted up to this excited state, and in fact, near this interface, the conduction band minimum energy changes, and it actually gets lower, and so there's a driving force for that electron to come to the surface so that it can do this kind of chemistry. Only within a certain width, called the depletion width, of this interface. So anyway, the idea is that you will have some energy associated with that electron at this interface, and that energy needs to be above the or more negative than the reduction reaction potential. So what we're going to see on a slide is the results of a lot of work that show how we can calculate these conduction band edges in the presence of water in order to then compare them to these reduction potentials on the same scale. And so we want to make sure that the energy that's right here at this interface is larger, more negative than the reduction potential of whatever reaction we're looking at. And so we've done this over a series of different kinds of reactions. I'm only going to show you the one that's the most plausible reaction. If we were going to look at photoelectrochemical water oxidation, we're not going to because we already looked at electrochemical water oxidation, then we have the same issue on the anode side, where in this case we want to have the hole, the absence of the electron, drifting to this interface to be able to strip electrons from water. So there's also work we've done on that, but I'm not going to talk about it. That's all thermodynamics. That's necessary but not sufficient condition. As I mentioned already, we've just talked about how to do electrocatalytic water splitting. But what we also need to be thinking about is kinetics, which of course we want these low overpotentials that we've talked about already, and those are associated with the kinetic barriers. In general, we have as a metric that we're looking for reactions that will have a barrier of no more than half an electron volt. So of the order of 10 to 12 kilocalories per mole, 50 kilojoules per mole, at room temperature. So that the reaction can actually go at room temperature. You need something that's a barrier that's not much larger than that. Okay, so I'm going to summarize in one slide some experiments that are key experiments and conclusions of things we've learned from them. Turns out there are very few electrodes that do this kind of catalysis, and none of them do it very well, hence the need for R&D. Okay? And one very interesting set are these particular semiconductors. that can take CO2 either to methanol or to formic acid, and they do it in slightly acidic water, so pH of 5.2, and it only works selectively in the presence of about 10 millimolar pyridine. So it's really interesting, right? It's just this interesting concoction, and the question is, we wanted to understand why that particular concoction. So very selective. That's extremely unusual. If you don't have the pyridine, you don't get the selectivity. So pyridine is clearly playing an important role. You don't get the same products. And the other thing that's amazing is it operates at underpotentials, which when I first heard that, I thought, what on earth does that mean? Well, what it means is that you don't have to apply the full thermodynamic voltage associated with the reaction, because the rest of the energy is coming from the light, from the excited electrons. So that tells you it's being driven by light. The overall efficiency, I said, is very low. So even though it's highly selective, and I should point out, you'll read it in papers, it'll say, great Faradaic efficiency. And in fact, that's true in this case, like 96% Faradaic efficiency. That's just referring to selectivity. It says nothing about activity. And so it's very important to work on this and to understand the mechanism. The mechanism is highly controversial, and so we spent a decade, I guess, I don't know, a long time, lost track of time, yeah, close to a decade, working on this problem, trying to understand every aspect of the mechanism and how to improve efficiency. And I'm going to tell you the end of the story there, or close to the end of the story. Anyway, relevant experimental observations. Underpotentials only observed when pyridine is added. I told you that. So a pyridine-related species must play a role. If the preferred pH is 5.2, if the pH is greater than 7, you don't see anything useful happening. And that just means that you need protons around. Okay, not surprising, because you need protons and electrons to do the reduction anyway. The interesting thing is that the pH is of 5.2 that is optimal in this situation is very close to the pKa of pyridinium. So most of the people in this audience, I assume, are chemists. And so, in fact, that should immediately clue you in, if you've taught freshman chemistry, that you're dealing with almost a buffer solution, right? pH equals pKa. So what that means is that you have nearly the same concentration of pyridinium as pyridine in solution. So pyridinium may be playing a role, so you have to think about that. The other interesting thing is that the reduction, as I said, only occurs on a few of these surfaces. And that then says, is the surface playing an explicit role through heterogeneous catalysis? Or is it just that it has the right band edge positions, these particular materials, to do such that the electrons are at the right energy state to be able to do the chemistry? And so we wanted to understand, is heterogeneous catalysis part of it? So in order to understand that, we had to characterize the nature of this electrode-electrolyte interface. And what I'm showing you here is actually a joint effort between me and my husband's group, Bruce Kale. And this is actually ambient pressure X-ray photoemission, showing that actually related to some predictions that we made first, looking at what happens when gallium phosphide is exposed to water. And it turns out that when gallium phosphide 110, which is the most stable and also the most active surface of gallium phosphide, is exposed to water, you get actually heterolytic dissociation of the water spontaneously when there's enough water such that you can make hydroxide that datively bonds to the gallium empty orbital, and the proton goes to the phosphorus lone pair, and you have water that hydrogen bonds to that hydroxide. So you make these sort of clusters of water and hydroxide. And we had made that prediction, and then Bruce's group went off and measured it, and this is the experimental evidence for it. So it turns out that then there haven't been experimental measurements, but we went and then looked at water on cadmium telluride and copper indium sulfide, the other two electrode surfaces, and in fact, we predict that water doesn't spontaneously dissociate on those surfaces, and that actually has profound implications for the level of those electrons. The interface changes because you don't dissociate water there. So now I'll show you some results of the calculations that will allow us to determine that conduction band edge with the electron energy. And this is getting at what is the role of pyridine. We know pyridine has to play a role here. We looked at a whole variety of species. Andrew Beckersley, my colleague at Princeton, had done some of the key experiments in this area, and he made what I consider to be a fairly preposterous suggestion that you make what's called pyridinyl. So you add a hydrogen atom to pyridine. Pyridine doesn't like that. You know, pyridine is aromatic. It doesn't like to add a hydrogen. So anyway, we set out to check that hypothesis, also looking at dihydropyridine, which is a stable molecule, and then also finally looking at this not stable, but we think metastable, 2-pyridinide, which is in fact deprotonated dihydropyridine. And so I could give a whole lecture on that. I'm not going to do it. I'm going to tell you that in the end, what we found is that the one species that could be reduced on gallium phosphide, cadtel, copper, indium sulfide is in fact, you could make 2-pyridinide. And that's shown by these conduction band minima in red, and the reduction potentials are shown, the most accurate calculation is shown as in this light blue. It's below the, it is, as it should be, below the energy of the electrons that are photoexcited. So this is the only feasible intermediate. We knocked out all the others over a period of years that could possibly be playing a role. And so then we went on from there and said, okay, so you can make this. Is it a bystander, or can it do the chemistry? So we wanted to check, can you in fact now, if you make 2-pyridinide, which is essentially adding a hydride to pyridine, can that then deliver a hydride to carbon dioxide to make formate? And so this, we wanted to compare it to what happens if, well, we showed you there's hydrogen on the surface from heterolytic dissociation of water. So could it be that hydrogen directly from the, dissociates from the phosphorus and goes to CO2 and makes formate? Well, that turns out to have a very high barrier, about 3 times the level at which we think is acceptable for this chemistry to be happening. So we don't think that's happening at all. That hydrogen, once it's on the surface, is stuck. On the other hand, there was another group, Charles Musgrave had proposed the idea that maybe dihydropyridine in solution could do this chemistry to produce pyridine and formate. And both he and I calculated a number that's, again, it's lower than hydrogen on the surface, but the fact is it's still too high. And in fact, it's favorable for the dihydropyridine to absorb on the surface. And once it absorbs, it's even more stabilized, and then the barrier is even higher. So these are barriers. These should not say delta G, actually. It says delta G act. So these are free energies of activation. So these are not the mechanisms. On the other hand, if you look at this 2-pyridinide here, here's a picture of it, and you ask, can it make formate, and what are the barriers? We looked at all 3 surfaces, and all the barriers are essentially within reason. In fact, what's interesting about this result is that we predicted that on the 111 surface, the barrier might be a little bit high, and if you go to this 110 surface, it drops in half. And the beauty of that is that Andy Beckersley has frustratingly unpublished data. It's in a PhD thesis. We've been trying to get him to write it up with us. But the fact is that what they showed is that if you etch the gallium phosphide 111 crystal, you make facets of the 110, and the rate increases dramatically. So this is consistent with that result, and it's the only species, again, that seems to be possible to be making this. I need to check the time. Okay, I'm doing all right. So one of the things that's really important to realize is that this species, of course, the immediate criticism of everyone in the audience should be that that's a very unstable species. How do you know that there aren't going to be side reactions that are going to take it out of action? And in fact, we know that under the conditions that the experiments are run, you only make a little bit of methanol. So probably there are side reactions. So let's take a look at them. So what we wanted to understand is, in some qualitative sense, what is the lifetime of the 2-pyridinide? And that's clearly, this species would love to be protonated to make dihydropyridine, okay, which is a stable molecule. So the question is, what's the barrier to protonate the 2-pyridinide. So we created a model of the 2-pyridinide with the surface that we know from experiment is formed, which is this half-dissociated water, heterolytically dissociated water with monolayer, and then with an eigencation to represent a proton source. And then we looked at what happens when this 2-pyridinide is next to a water versus next to a hydroxide, both of which exist on the surface. And it turns out that in either case, the water and the hydroxide will hydrogen bond to the nitrogen in the 2-pyridinide. And then these arrows are showing you essentially how the protonation occurs. And if there's water, it protonates immediately. There's no barrier. But if there's hydroxide, it turns out that again, the mechanism isn't simple. It undergoes a concerted proton transfer in the case of the hydroxide with a barrier of about 0.3 electron volts, which is similar to the barrier for hydride transfer to CO2 and to make formate. And so what that says is if you could possibly create a surface where you have, obviously if you're not doing anything, you're going to get some statistical distribution, and so many of the 2-pyridinides are just going to be protonated on the surface, but some of them may live long enough in order to, again, essentially transfer the hydride. And so that's the hypothesis, because it's the only game left standing at this point, game in town. So and that may help us understand why you have to have this kind of intermediate pH. It's not too acidic. It's not neutral. It's not basic. The other thing that's really important to test is whether the 2-pyridinide could produce H2, because you could imagine that the eigencation could just pluck the hydride off and make H2. If that happens, then we've killed our hypothesis, because we know that this combination of pyridine and light and the semiconductor doesn't produce H2. It's highly selective, only for making methanol. So we did calculations. This was done by a postdoc of mine, Shenzhen Xu, and showed that the barrier, the free energy barrier, in fact, is very high for for making hydrogen. And so that's consistent with the selectivity, which further is validating this as a potential transient intermediate in this chemistry. So, of course, then the next thing a critic should say is, you just made formate. What are the barriers to make methanol? And what's the barrier to making methane after you make methanol? So Shenzhen went off and did these calculations, again, with the hypothesis that the 2-pyridinide is the key species. And so this is just a cartoon showing you that number that we had already calculated, that you can take CO2 to formate and formic acid. There's no barrier to make formic acid from the formate. That overall barrier is very low. So then the question is, how do you go ahead and go on? Well, what we showed through a series of calculations reported a couple of years ago now is that you can make dihydroxymethane with low barriers. And then actually the hardest part is something that has nothing to do with the pyridine, okay? Which is that this is known, we didn't calculate this is known experimentally, that you can dehydrate dihydroxymethane to form formaldehyde, and that barrier, free energy barrier, is known to be about 0.6 volts. That's just with electron volts. So that's just within the noise of being able to be reachable at room temperature. So the interesting thing is then we showed that you can't go directly to here. This is the high barrier to go from the dihydroxymethane to methanol. But if you go through formaldehyde, either in solution or on the surface, you have a very low barrier. So the surface so having the 2-pyridinide on the surface and then either and reacting with formaldehyde rather than the dihydroxymethane is the key to making methanol. And then he went on to show that there's a very high barrier to take methanol to methane. So that explains why you don't go to methane and why you end up with methanol. So to summarize this many years of work by many people in my research group, what is the overall picture? And you can read about it actually in this Chemical Reviews that has a lot of other people's work as well on CO2 reduction. And basically what we believe is happening is that you get a 2-electron, 1-proton process. It's this hydride process that we've shown is feasible under illumination on all of these semiconductors. And essentially, once you make that, you can very fastly transfer hydride to form formate. The barriers are all reasonable. And so the role of pyridine is that you need the pyridine in order to create this transient state for the hydride. If you have hydrogen on the surface, it's very different than on a metal surface where you have a hydride that then can do chemistry from the metal. It's so strongly bound to the semiconductor that that doesn't happen in the case of gallium phosphide. And so in this case of gallium phosphide, what the pyridine is doing is essentially providing a place for the hydride to form. Okay, that it can't be transferred from the surface. It has to be that you get 2 photoexcited electrons plus a proton from solution to form this 2-pyridinide. And it's clear that dihydropyridine and adsorbed dihydropyridine, well, that's what the asterisk means, that it's adsorbed. They're both inactive, have 2 high barriers to do the chemistry. I didn't talk about how we actually did very careful studies to show that you could to calculate the barrier to form this, not just the thermodynamics. It's also, roughly reasonable. We talked about the lifetime of 2-pyridinide based on thinking about protonation to dihydropyridine versus hydride transfer kinetics, comparing those 2 barriers. So you have two different possible pathways, and you want to make sure that they have at least comparable barriers so that the hydride transfer can continue. We also showed that the barrier to form formate is much lower than to form hydrogen. That's consistent with the known selectivity. And I showed you that the barriers to form these species on the way to methanol are even lower, whereas the barrier to form methane is much higher, and that explains why you get methanol selectively and not methane. Didn't talk about this, but we can understand potentially why on CAD-TEL you make formic acid. Anyway, that's a bunch of explanations. What good is it? What can we use it for? And so the idea is, coming from what we've learned, we can have some design principles potentially to enhance rates. And I think, given the time, I'm definitely going to end on giving you just this last set of ideas. So the design principles to enhance rates. Well, what we really want to do is find a way to stabilize that 2-pyridinide. But again, a Goldilocks situation. We want to stabilize it, but not to the point that its reactivity doesn't become so good. And so we want to play with essentially the electronic distribution on the 2-pyridinide. And the way you can do that is by functionalizing the pyridine or by substituting some other metal cation for the gallium. And so that's what we looked at. You can also play with pH. We didn't do that in these simulations, to balance, to see that you can have hydroxide rather than water next to the 2-pyridinide. And so that potentially could give you more 2-pyridinide that survives and hopefully optimal hydride transfer barriers to enable a faster rate. And so what Shenzhen recently did was to essentially look at this idea, surface doping and molecular functionalization. And the idea is that if you have a less negatively charged 2-pyridinide, then it's going to be less likely to protonate. But if it's less negatively charged, it becomes less hydritic, and so it will have a higher barrier to hydride transfer. So we want to compare the protonation to the hydride transfer, and that's what he did in our most recent work that just appeared a few months ago, and that is to look at both substitutional doping and functionalization of pyridine, and to compare the hydride transfer barrier. Here, this is doping at the gallium site where the pyridine is attached to the protonation energy. We're trying to get this protonation energy to be less exoergic. And here we have an example then for functionalization of pyridine, a bunch of different substituents. Haven't told you, we looked at meta, para, ortho, we looked at everything, okay? This is just showing you the best results. And what's in green is the part that obeys this rule that says what are the pieces where we could have a lower hydride transfer barrier that doesn't cost too much in terms of, that also works with whatever protonation energy we get. And so the rule is that the protonation exoergicity reduction, because we're trying to make it so that it doesn't want to protonate, so we want to move it across to the right, must be larger than the hydride transfer barrier increase. Okay? And it turns out that's the green regions. And so it turns out that you can see that you can move the needle on by doping with titanium quite a bit without paying a cost in the hydride transfer barrier. So we think that it's worth thinking about, is there a way to dope gallium phosphide at the surface, not easy, with titanium? A much easier thing for an experimentalist to do is to functionalize pyridine. And so what we see here, again, the best result is this fluoroethyl pyridine that we think should in fact enhance CO2 reduction to methanol. So I am always not happy with people who go long, and so I am not going to go long. But what that means is that I need to unfortunately skip the last topic, which was only 3 slides, but anyway, I'm still going to skip it. And I'm going to end with this. Oh, wow, that's weird. Oh, no, it's fine. OK, except that it's not showing. That's weird. It's not showing the very top. Whatever. I'll tell you what the very top says. It says, vision of a sustainable future. OK? So we have to find ways to use sunlight, air, water, and carbon dioxide, which we have in abundance, and catalysts, use our precious knowledge of chemistry and material science in order to figure out how we're going to survive without fossil fuels. So clearly, sunlight for energy, or wind for energy, that's for electricity. So electricity via solar cells or wind turbines. I'd like to see fusion in the mix at some point, but it's a long way off. Chemicals and fuels via photoelectric catalysis, like we've talked about today. I didn't get to talk to you about this, but we have work that actually was recently publicized on the UCLA newsroom about using plasmonic metal nanoparticles for the latest work is looking at dry reforming of methane to syngas. The beauty of that is you take 2 potent greenhouse gases, CO2 and methane, and you convert them to syngas that you can use for other things. You can also split nitrogen, or at least we believe that. We've predicted that you can. That hasn't been, there are some experimentalists that are now trying to take our doped metal nanoparticle idea and see if we can make that happen. But you can split hydrogen using these plasmonic metal nanoparticles. And so it could be a route to make ammonia, which could be used then for fertilizer for food. I talked to you already about renewable electricity plus electrochemical water splitting for efficient water oxidation via these inexpensive catalysts. The protons that are released from that water oxidation then can be used to make renewable hydrogen, so you can drive a hydrogen fuel cell car from Toyota without feeling guilty. Or you could use the protons to reduce CO2 at these pyridine functionalized semiconductor electrodes to make carbon-based fuels, because we can turn methane into gasoline. We know how to do that with zeolite catalysis. And so that's a way for us to have a sustainable, virtuous cycle. And unfortunately, what you can't see is the very last thing, which is showing on here. So I'm going to take it out of slideshow so you can see it, hopefully. Does it not do that? Hopefully it'll do it. Oh, that's very sad. OK, so what it says is final grand challenges is sustainable water desalination, and also essentially carbon what's called CCUS, which is carbon capture, utilization, and storage. So that's I feel like the next. Oh, there it is. Wow, why? OK, that's very inconsistent that the technology didn't work the same way. But there it is. And so I was a co-author on this review article about CCUS that came out of a workshop that I co-organized with the Royal Society and the National Academies. And so if you're interested, it lays out what are the what are the challenges associated with essentially dealing with carbon dioxide at scale. So those are the things that I personally want to start working on those, especially given what we're all seeing, especially in Southern California with wildfires. I will end on a personal note to say that it was a huge shock for me to come back here after 15 years and understand that there's something called a fire season. Didn't exist when I was here before. In 21 years of living in Southern California, first as a grad student and then as a faculty member here for 16 years, I experienced one fire, 1993 Malibu fire. Since I came back in 2 months, I experienced 3 fires. This is really, it's now becoming trite to say a climate emergency, so I don't even want to use that language, but everyone in this room has talent that can be brought to bear on these problems, and I urge you to do so. So with that, I want to thank Mark again, who's in the audience, and please, you should get to know him. He's fantastic. And so for the water splitting, it was done by, the work I talked about was done by Mark. We have a paper coming out in JAX that just got accepted by Mark and Ananth on water splitting. The stuff I didn't get to talk about at the end, the plasmonic photocatalysis that uses our embedded correlated wave function methods, is done by Mark and also by Lucas Bao, another postdoc. These are former students and postdocs in my group who contributed to the CO2 reduction story that I told you about. And then these are my current postdocs working on CO2 reduction. And I need to thank my experimental collaborators. And I also have to thank profusely the Air Force Office of Scientific Research that has funded my work since I came here as an assistant professor. I wrote my first proposal while I was a postdoc. Bill told me, don't use your postdoc to write proposals. I don't know if you remember that. You said enjoy it. And I still wrote proposals. I didn't listen to him. And I had a bunch of grants walking in the door. And I was off to the races, which was great. And the Air Force Office of Scientific Research funded every single part of what you heard today. Thank you very much. I apologize I went over.
No, will you take some questions?
Sure.
I was interested in the iron-doped nickel hydroxyoxide catalyst. Have you done the opposite way of nickel-doped iron hydroxyoxide, and what's the ratio of nickel to iron?
We have not looked at iron as a host. As I said, the iron has a fatal flaw. It does not want to be reduced because it's iron 3, it's extremely happy. So that's just not a good plan. So what we've done instead, and the work is we've submitted an invention disclosure and a provisional patent because we think we have a very nice idea of a ternary oxide that potentially can improve upon the iron-doped nickel oxyhydroxide by looking at the principles that we have here. And stay tuned in the sense that the papers are submitted and you'll be able to see what those are about. But essentially, we think that there are certain dopants that you can add to the iron-doped nickel oxyhydroxide that will help it be even more efficient at oxidizing water. Okay, so I'm sorry I'm not being more specific right now.
Yeah, Professor, I have one question about the last part when you said the pyridine adsorbed on catalyst. So why it is specifically only on these 3 catalysts? Because any catalyst that will absorb pyridine, it can do this thing, right?
Well, it's a delicate balance. And pyridine, so you mean by any catalyst, you mean like platinum, for example, or something like that? Is that what you're thinking?
The semiconducting catalysts that have similar balance, like let's say like what you mentioned.
Yeah.
As gallium phosphide.
Oh, okay. So a compound semiconductor, you're saying, some other one. Yeah, it's potentially possible it could work with other compound semiconductors. We only looked at those 3 because those had been looked at experimentally. Okay. So there isn't, what's clear is that you need, it's a Goldilocks situation, right? You need the right stability, you need the right band edge, and you have to calculate that. We learned over time the best way to refine how to get that band edge right, to have the right model to get it as accurately as possible. So you have to, because that conduction band edge determines the energy of the electrons so that you can know whether you have the right thermodynamic driving force. And then you have to look at the kinetics. So you just have to, there's no, other than saying that we know what the constraints are based on the thermodynamics, and we don't know there's no way to predict yet to go out and say, aha, I'm sure that this will work. We have to go and model it and see, unfortunately. It's not, we know what the metrics are that are key in terms of stability and what we need to look at, and stability and reactivity and the positions of the band edges. We understand all of the properties we need to look at, but it's not turn the crank, that's for sure.
Sorry, just 1 second. Following up on that
Yeah.
question, you're talking about what properties the catalyst has to have for this purpose. But the pyridine, you know what properties it needs.
Yeah.
You talked about them. Could you design other molecules to test your hypothesis that have those properties that would play the same role?
Yeah, in fact, it's known. I mean, so first of all, well, we did that in the sense that we looked at substituted
You're
pyridines.
functionalizing
Yeah,
or substituting
Right,
pyridine, but
right.
what about starting from scratch?
from some other molecule. Well, so the key is to understand. So I will say that there was a beautiful insight in a paper that was co-written by Charles Musgrave and my former my former postdoc advisor, Casey Hines, who is a person of great insight. And what he pointed out is that the thing that is very special about any of the species that you think about is that there can be a great driving force to recover aromatization. So to think about, because that's what happens, right? The hydride transfers, you've got pyridine back. So there's got to be some way to think about, what other, of course you could think of benzene or something like that, but benzene is not going to work because you need something that can be attached to the surface, okay? Because it's got to be able to accept electrons that are coming from the photoexcitation. So the beauty of pyridine, or in fact, Andy Bacarsley looked at imidazole, so there can be other kinds of aromatic amines. I'm agnostic. It can be an aromatic amine. It can be any kind of aromatic species that will bind strongly enough to the surface that it functionalizes it. That's what I would say. That's the key.
So this is also following up on that.
Yeah.
Which is, I'm not sure I fully understand the role of the inorganic in terms of the semiconductor. The band edge was way above the pyridine level in some cases and right next to the pyridine level in other cases. And so is it the strength of the native bond between the pyridine and the surface that is modifying the reactivity? What component of the inorganic reactivity is having the biggest effect on
Very
hydrogen
little.
transfer?
Very little, as it turns out. I mean, that's the thing about, that's why it was so cool to do that Shenzhen, my postdoc, did this study of surface doping. Because in fact, what he showed is that you could get just a very slight improvement by changing the species to which the pyridine is absorbed, okay? So that is not particularly helping, okay? So, which is good because I think it would be really hard to do, frankly, to make sure that you substituted just at the surface layer. It's not trivial. Oh, good, all right, fine. But it's clear that doing this functionalization could lead to a pretty hefty change in that trade-off. So that's what we're currently hoping somebody will do.
Emily, thank you for this very exciting and inspiring talk. I see there are more questions, but I also see some people leaving. Let's adjourn to the lobby and ask more questions and talk with Emily and each other at the reception.
Oh, wait. Oh.
No speeches. Here you are.
Oh, okay. Thank you.